Okay, so in this section, we are repeating the whole thing of rate of change using the differentiation of trigo, exponential, and ln. So the steps doesn't change. The notation also doesn't change. So if you still remember, in the basic rate of change, we got a basic formula like this. So we can still be using the basic formula. Okay, so just as a recap, this is the rate of change of x. And this is the rate of change of y. So the formula doesn't change, the notation also doesn't change. The only thing is your dy dx. So you gotta go according to the formula of dy dx. So in our case, in first question, if you look, it's a ln differentiation. It is a ln and it is with quotient rule. So you perform your quotient rule to get your dy dx. So you need to be able to do the quotient rule correctly. And then after that, let's understand what the question giving us and what are we finding. So our job is to find dy dx. And this 1.2 is actually the rate of change of x. So we are given this. We are supposed to find dy dx, dy dt when x is 0. So maybe you want to explore what happened when y is 0. Sorry, just now I mentioned x 0, right? So when y is 0, what happened? So y is 0. So where is your y? This whole thing is your y. So change out this part to 0. So when you change out this part to 0, okay, you got a little bit of logarithm to do. So this part is log base e. Some of you may forget that this part is log base e, and how do you do that? You change it to index form. That's how I gotten this. And e to power 0 is 1, so I actually get 1/4. So eventually, I'm supposed to find my dy dt when x is 1/4. Then I'm going to use back my generic formula. So this is the generic formula that we always use in our dy dx. So we still do the same thing. So I'm going to insert the dy dx that I have found. I'm going to insert the x dt that I have found. So I got a very nice huge fraction. So it's just 1.2 multiplied to the fraction. And I just put in my 1/4 inside. That's it. And then you punch calculator. So the steps are the same, except that this time around you realize your differentiation is quite long. So some students, they actually lost track because they spend a lot of time doing the differentiation. They focus on the differentiation, and after that, I don't know what am I supposed to do. But the generic formula for rate of change doesn't change. Okay, so hopefully you see a bigger picture in this way. So we're going to repeat the same thing. We're going to repeat the same thing in D2. Okay, except there is a trigo differentiation. If it's a trigo differentiation, it has to be in radial mode. Same like what when you are doing tangent normal. And this value here is your dx dt. And our job is to find dy dt when x is pi over 3. So this is my aim. So obviously I do my dy dx first. So in this case, the dy dx is the one that involves a chain rule, because sine square x is sine x with a square. So you got to do a chain rule. Bring down power, minus power, differentiate inside. So I just need to do a chain rule to obtain my dy dx. Then I go back to my generic formula. Generic formula. So my generic formula, I gotten my dy dx already. My dy dx, and then my dx dt. Then I multiply them. Then I just need to put into punch in my x equal to pi over 3. So again, right, if you're punching, right, punch one by one. Don't punch the whole thing. So sometimes they will ask you to leave it in terms of thirds. So again, this one is the special angle. So this one gave you the root 3 over 2. And then this part here, it gave you half. So usually I don't press everything. So a lot of you will just input everything in your calculator, then you will be asking me. So I got a chain of decimal. If the question they didn't ask for leave it in the exact form, your chain of decimal is okay, you can get a 3SF. But if the question asks you to leave it in exact form, then you got to leave it in thirds. This is called exact form. So in O-level, there are some questions that require you to leave it in exact form. That means they don't allow chain of decimal, especially when it involves a special angle. Okay, so the same thing happened here. You realize that it's an exponential differentiation. So this part, what is difficult on this part is this tiny part. A lot of people forget that it's actually a product rule. When you try a dy dx, they will actually forget that that's a product rule. So the product rule is only applied on this part. So some of you will be thinking, like one part is product rule, and then the second half here is just normal differentiation. The normal differentiation referring to this one. So you just differentiate like, so the normal differentiation of exponential is here, the ax plus b. So the first part is a product rule, the second part is the normal differentiation. So all in all, this is how you got to do the differentiation. And then you go back to the same thing again. Go back to the same thing. Go back to the same thing. What is this rate? So this one is the x dt. And your job is to find dy dt. Your job is to find dy dt when x is 0.5. So back to the generic formula one more time. Back to the generic formula. So use your whole dy dx multiplied by the dx dt. Dx dt is 3. And then you just put in the x. To get the answer. So in a nutshell, the steps are similar, but because sometimes the steps are quite long, it will make you lose track. Okay, so like sometimes even when you put in the x equal to 0.5, you will take a bit of time to calculate. Okay, so sometimes, or here in this case, right, in the first place, maybe you will do all your steps correct, but you didn't realize that your dy dx is wrong. You didn't realize that the first part actually needs a product rule. Okay, so please take notes of the various way of differentiating depending on the question, but if it's rate of change, the generic formula of rate of change doesn't change. Okay, it's only the dy dx change